One-to-one linear transformation is called a what if it maps a vector space V onto a vector space W? Isomorphism. If you said isomorphic, that's fine. The word is isomorphism. Yeah. But, okay, the vector space P3 is isomorphic to R what? 4. Good. We'll talk about Y in class today. The mapping X goes to the coordinates with respect to beta is called the coordinate mapping determined by beta. Okay. So remember we talked about what a basis was last class, and it was just a set of vectors that spans the entire space and is linearly independent. So there were 2 criteria for being a basis, which means that you can often come up with more than one basis for a space, right? Okay, so let's look at 2 different bases for R2. Okay, the standard basis is called 0, 1, 1, 0, and 0, 1, right? That is a set. The set of those 2 vectors spans the entire space, because you can create any vector in R2 as a linear combination of these 2. So it spans the entire space and it's linearly independent. That makes it a basis. But here's another basis, right? 1, 0, and 1, 2. Gamma, yeah. Another basis, gamma. 1, 0, and 1, 2. So this also spans the space, right? Because you can create any vector in R2 as a linear combination of these 2 vectors. And they're linearly independent. So they're both bases for R2. And the unique expression theorem or something from the section 4.4, it says that any vector in R2 can be written as a unique linear combination of the vectors in a basis. So I'm just going to pick a random vector in R2, 7, 4. And I want to write it as a linear combination of the vectors in the basis beta. Okay, so what should my weights be? 7 and 4. And that's why it's called the standard basis. It's like the easiest one to use to write any vector as a linear combination of the 2. So this x beta, you would read that as the coordinate mapping, right? The coordinate mapping determined by beta gives us, if you just take the weights and throw them in a vector. So it's going to be 7, 4. So my original x and my mapping end up being the same in this case. So under the coordinate mapping determined by beta, the standard basis, 7, 4 goes to 7, 4, right? There's nothing fancy here when you use the standard basis. All right, but let's look at what happens if I use the alternative basis, which is 1, 0, and 1, 2. What do my weights have to be here so that I can take a linear combination and get 7, 4? 5 and 2, right? So my coordinates under the mapping gamma, right, under the basis gamma, is going to be 5, 2. Okay. So under the coordinate mapping determined by the alternative basis, 7, 4 gets mapped to 5, 2. All right, so let's think about how this works graphically. So if I want to plot a point in the coordinate plane, I want to plot 7, 4 under the different coordinate systems determined by beta and gamma. So if I'm going to use the standard basis gamma to get to the point x, you had 7 units in the 1, 0 direction, 4 units in the 0, 1 direction, right? So that's over 7, up 4. That's how we standardly graph things. Standardly, yeah. All right, but let's use the alternative basis. So the alternative basis says had 5 units in the 1, 0 direction and then 2 units in the 1, 2 direction. So first we have to determine what is the 1, 2 direction. So from my origin, if you go over 1 and up 2, and I draw this line, and then I keep going over 1, up 2, over 1, up 2. So these are units in the 1, 2 direction, right? So if I want to plot the point 5, 2, right, then I would go 5 units in the 1, 0 direction, so that's here, and then 2 units in the 1, 2 direction, 1, 2, and I land here, right? So the slope is obviously half. Mm. Or, sorry, 2. Two, yeah. Yeah. So that's what we have to go. That's slope. Yes. Yep. Yep. So this 0.52, right? This says 5 units in the 1, 0 direction, 2 units in the 1, 2 direction. Now, if you look at, I kept the original axes on here so you could see that using the coordinate mapping beta, right? This is actually at the 0.74. Like if you go over 7 and up 4, you land at that same spot. So it's just two different ways of getting there, right? Instead of using our standard X and Y directions, with the gamma basis, I'm using the X direction and then this other weird direction, the 1, 2 direction. The 5 and the 2 were the weights that we put on the alternative basis to get 7, 4, right? We said if you use the alternative basis, my weights are 5 and 2. So those are my coordinates of the point under that basis. Yep. Okay. Okay, so here I'm giving you a basis. You don't have to check that it's a basis. It is. Those 3 vectors form a basis for R3. If you wanted to check it, what would you look for? Linear independence and pivots in every row and pivots in every column. If you want it to span R3, right? A pivot in every column will tell you it's linearly independent. A pivot in every row will tell you it spans R3. Yeah. No, it's actually backwards because I am starting by giving you the coordinate vector, right? This is a vector of weights, right? Go back to what we just did. The thing we came up with was x sub gamma, right? That was the vector of weights. So if I give you x sub beta or x sub whatever, x sub gamma, those are just the weights. You just throw those weights onto the vectors of your basis. So this is going to be 1 plus 0 . I can't, guys, can you stop talking for a second? I can't understand your question. Oh, yeah. Yep. Yeah, so, and that's what we're going to do in part B, yeah. So when I put these all together, I'm going to get -2 plus -4 is -6. -5 plus -8 is -13. 7 plus -4 is 3. Okay, so that is my original x. This equals x. So that's in R3, right? This is the point in R3, my original point in R3, using your standard basis, right? And then I gave you an alternative basis here, right? And then I gave you the coordinates under the alternative basis, and those just mean what weights do I put on those vectors to get the original back. The standard basis is the identity matrix, yeah. The columns of the identity matrix. Okay, so the change of coordinate matrix from beta to the standard basis is exactly what Alex was just saying. So another way of doing this problem would be to take the vectors from beta and put them in a matrix. And if you multiply that matrix by your vector of weights, 1, 0, 4, you would get -6, -13, 3. So we call this the change of coordinate matrix. This is P sub beta, the change of coordinate matrix. Okay, so now I'm giving you an original x, 529. That's the standard, using the standard basis, like 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the point 529 in R3. I want to find the coordinate vector with respect to this other basis that I gave you, beta. Okay. So basically, I'm asking you, what weight should you put on beta to make x? Yeah, so that one I would augment. I would take my P sub beta, augment with 529, and that will give me the weights, right? So I already have this solved. You don't have to take your calculators out. 1, 0, 0, 0, 1, 0. Thank you. 0, 4 thirds, -11 thirds. That is my x sub beta. Okay, so.
Wait, why is it, okay, so when we find x, we want to find the weights for x, but we want to find the vector. That's what we all do.
Yeah. So when you want to find the coordinate vector, that's when you're looking for the weights, right? So I wanted to know what weights should I put on these columns to create 529. So I would solve this system of equations to figure that out. Yep. And then if you know x sub beta, like we did in part A, I gave you x sub beta and I just wanted to know x, then I've given you the weights. So you just throw those weights onto the basis vectors. Nope. Well, I mean, we've solved many things by augmenting and row reducing, right? Yeah. Yep. A is the change of coordinate matrix. Yeah. B is your x. Yep. All right. So I would like to do this same problem again. Find the coordinate vector x sub beta for the vector 529. But this time I want to use an inverse matrix. Okay. So I'm actually going to write down some things that maybe I should have written down in C to show you why we do the augmented matrix and row reduce. So I'm looking for the weights that I have to put on my basis to get 529. That's what the coordinate vector does. So I want to know, I'm looking for my weights x1, -5, 7, plus x2 times 1, -4, 4, plus what other weight to go on the third vector of my basis. Okay, so what weights should I choose to get 5, 2, 9? That's what the coordinate vector is. It's the weights that you put on the basis to make your vector. Oh, right. So this is what we call a vector equation, right? I could translate this to a matrix equation by taking each of my vectors and putting them in a matrix. This is why I made you do so much translating in the beginning of the class. We had so many ways to express the same thing. So my matrix equation, I put my unknowns here, x1, x2, x3, and that equals 5, 2, 9. So the way you solve, of course we've done this before, of course. Yeah, yeah. So the way you solve that is you set up an augmented matrix and row reduce, right? Or multiply both sides of this equation by the inverse of this matrix.
end up with the identity matrix. Right?
Yeah, so the inverse of a matrix times the matrix gives you the identity. So yeah, I'm going to multiply both sides of this equation by the inverse of that matrix. So first I need to get the inverse of that matrix. I'm just going to have my calculator do it. Yeah. All right, so to get the inverse of that matrix, I go into matrix here. I put in a 3 by 3. 3 by 3. -2, 1. No, 3 by 3. -1. -5. -4. -2. 7, 4. -1. Yes, you're right. Sorry. 1. All right. So then go back to matrix. Oops. Math, RREF, matrix A. All right, so my inverse matrix is ugly. I'm actually just gonna, no, all right. Okay, so my inverse matrix is this ugly thing. -4/17, 19 over 51, -8 over 51, 1/17, -3/17, -5/17. 2/17, -1 over 51, -13 over 51. All right, so that's my inverse matrix. When I multiply that times the change of coordinate matrix, I didn't want to write that all again. This is, this matrix here is P sub beta, and this matrix here is P sub beta inverse. It's P sub beta. Beta is just the basis as a list of vectors. P sub beta is the change of matrix, change of basis matrix.
So we do it this way.
Yes. P times 529. P sub beta inverse is this whole matrix. I just didn't want to write it again. So I wrote it as P sub beta inverse. All right. Yeah, you can do it the other way. I just wanted to remind you there's another way to solve a matrix equation. So P sub beta inverse times P sub beta is the identity. So, and then the identity times a vector just gives you the vector x1, x2, x3. And then if I multiply P sub beta inverse times 529, I'm not going to write that out. I think I already did it. Yep. You get 0, 4/3, -11/3. Same thing we got using the row reducing approach. All right, so here is where coordinate vectors comes in super handy. Is like last class, I think it was Rob when I asked you to like think about P3 as a vector space, and you were like, I don't want to, right? Yeah. So here's what coordinate vectors are awesome for. They can take all those weird vector spaces that where the elements aren't actually vectors, we just call them vectors because they act like a vector space, and you can actually turn them into regular vector spaces, like R something, right? So consider P3, which is the set of all polynomials of degree 3 or less. The standard basis for P3 is 1t, t squared, and t cubed. Right? To make any polynomial of degree 3 or less, you would just throw weights on those 4 polynomials, and you get some element of P3. So a typical element in P3, right, would just have weights of A0, A1, A2, and A3. So my coordinate vector is just the weights, right? So it's just a vector of my weights, A0, A1, A2, and A3. Right? What space does that vector live in? R4. Yep. So now you could just use the weights that are on the standard basis, or think of them as the coefficients on any element of P3, put them in a vector, and now you can just treat it like you're in R4. You don't really have to think about polynomials anymore. First, just translate it into a vector of weights, and then you can answer whatever question I asked you about P3 by answering that question about R4. The answers will be the same. That's what isomorphic means. It means that P3 and R4 act exactly the same way, right? So if I ask you a question about P3, translate yourself into R4, answer the question there, the answer is the same in P3. Yeah. Okay, now you have some stuff to do.